Good afternoon, ladies and gentlemen, and let me welcome you all to the SAIEE house this afternoon. I believe there might be others that might be still stuck in traffic, but yeah, we will get there. And I am told that we have a live audience of, at the time it was about 70, so let me also welcome them. And let me welcome you all to the inaugural, the very first SAIEE Technical Talks event. This was scheduled to happen last month, and as with everything, all good intentions, things will go awry, but here we are this afternoon. And let me, whilst I'm at it, do the necessary. First and foremost, emergency. In case of any emergency, there are 2 exits to my right. Should the siren sound, we will go out through there and through the aluminum doors to the right into the parking area, where we'll then meet so that we can then see if everyone is accounted for. And when unfortunately that does happen, we'll just have to make sure that we all come. Ladies, please remove your heels so that there won't be any injuries. Okay. Onwards with that, whilst we at it, the idea, if I can just delve a little bit with the idea as to why we're here. This was, initially the idea was to then go back to what we are as the SAIEE. What we are a networking platform, and that's primarily who we are. And these SAIEE technical talks were then initiated so that we can get back to basics. We need to once in a month meet and have technical talks in whatever the different subject. Now, the subject for this month is on lightning, and these are then meant to coincide with the theme for that upcoming What Now item in that magazine. So there is that congruence. So to that effect, let me thank the Lightning Gurus who actually have sponsored this event. And please, round of applause. Thank you very much. Thank you very much for taking the leap. Somebody has to take the first leap, and really, we appreciate that very much. So to that effect, we will have Alexis Barwise, who's going to be giving us the very first talk. And let me just hand it over to him. And thank you very much, ladies and gentlemen. Welcome.
Good afternoon, goeiemiddag, guten Tag, Herr Beutel. Thank you for being here. Thank you for giving us the opportunity. It is always so nice to talk about what we love. This morning I was talking to some electricians at Sasol, training them, and I was telling them that the Seronophile is a person who loves lightning and thunder, and this is, amazing for us. And one guy said, isn't that the crazy people that run around outside in the evening? I said, well, that's the same thing. We've embarked so much on, we've seen so much happening in the lightning protection industry, and it's just so, so daunting to see what we have to still do, but yet so exciting to see that there's a big movement. And I'm just so glad to have been part of this. I'm glad to share with you today at least what we have seen and learned, particularly in terms of innovation. Thatch roof is only the application today, but the innovation itself can be used in many other applications. I'm going to talk to you primarily about what has happened in thatched roofs. Why are we seeing issues? And then we're going to talk about what's letting us down. And so we will see what the standards have had to do and why we have a working group rewriting the standards at the moment. Why we have to then look at how to start regulating and or in some or other way share this information, because it's all compounding it. We can only be as good as our designs, but our designs is only as good as our installations, right? And so we have this issue at hand. Give you some examples on that and then share with you the innovation itself. A bit of a background is just to remind us all that when lightning is striking, it's but a discharge between the clouds, let's say in most cases a negative base, coming down to Earth, as we know, and this downward leader right at the end, before it actually intercepts with the Earth, there's an upward streamer that's, let's say, engaging with, right? It's these two negative and positive attractions that is making this attachment of lightning. When we are using today in thatched roofs, we've got these normal freestanding masts. I think we've all seen them. We've grown up with them. It's just part of who we are. One could maybe even say, as we talk about heritage this week, masts could probably even be put inside that little bundle. But this attachment is made, and then we've got the transfer of energy from the cloud down to the Earth. Our problem today, as you see in this example, is that it's probably not too clear, but there's a mast on the left, there's a mast on the right, and yet the entire house is destroyed. And so the questions start raising, or the questions are raised to say, well, what went wrong? So in theory, we all know that the earthing system that is connected underneath this lightning mast, call it some other collector of the protons in this ground. So we've got all these collectors, and we get all these protons together, and then they rush up onto this conductive element and even rush out further than these conductive elements because they stream towards this negative lightning leader that is coming down. What we have in this case, though, is that it did not work, and we start asking ourselves, but why? What happened? What went wrong? In this case, we see that you might not see it on the picture, but this roof was covered with this chicken mesh, this diamond mesh, metal plate or metal, mesh itself. And they themselves then become an upward streamer to say, well, I also sense this downward leader coming, and then I will become the attachment. So we almost have a competition between a mast that was intended to do the interception and the chicken mesh or type of sheeting that's on top of this thatched roof. So one starts to think, well, if this one should win the race, if this one should be the intercepting point, then what's wrong? Is it the earthing system? Is it the mast itself? How is this industry working? Why is this mast not doing what it should have done? And we start looking at some of the examples. One of them, when we did a little case study, is that we actually, it was quite interesting to see the South Africans reply to rugby quite strongly, right? So we gave up some tickets for the All Blacks against the Springboks, and we found out through a lot of lodge owners, thatched roof owners, etc., that those that have lightning protection, 45% of the thatched roofs that have conventional lightning protection masts still experience lightning damages. That's a huge figure if you think about it. The mast should be there to mitigate the risk more than 90% at the very least. Then we see another shocking statistic, and I'll get a little bit into it, is that the increase of lightning is also seen and felt by all. National Geographic is stating that by 2025, the lightning increase globally would be 50%. That's a lot. South Africa is even worse right now, and we'll see that statistic. And then finally, we see but 91% of these homes that have masts never installed any other surge protection bonding requirements. So we also see that what we as engineers term a lightning protection system to be is in the market perceived as put up a mast. And so we start seeing some of our issues that we need to deal with. This is some of the recent, all of these are quite recent buildings that I've been involved with to see that in low areas, this is areas where lightning is used to not be high. Let's say used to be areas where an underwriter would say, and even maybe our risk assessments would come to the result to say, but we don't really need to mitigate. The risk is not that high. And yet, all of a sudden, in these low-lying areas, we see huge lightning damages. We see complete buildings burned down. And it only brings us back to the statement that lightning is increasing. What used to be a low-lying area has now become quite a high area. And I show the example with the CSR map from 1994. I live in Irene, and in those days it was about 8 strikes per square kilometer per year. And the reason was we had one station measuring the entire country. So one would say the data collection, even the data itself, was not that accurate, or at least it was as accurate as it could be. Then we had some interim data that we released in the SANS 10142 Part 1 update, as well as in the National Building Regulations. And we see all of a sudden, I mean, if you just look at the yellow parts, how much that increased, which is called medium to severe lightning areas. Look at that. That's a lot. And then we even take it further and say, but now for 11 years we've got data, and we see that this area has even become 12.1, which is Irene, right? And all of a sudden with better measurement, now 25 stations, we can even start seeing our little Drakensberg, you know, and we start seeing that lightning is definitely increasing. Look at this Kruger area, exactly where I said those low-lying areas used to be are now actual problems. So I said that our designs can be as great as we want to be, but an installer has got to be the one that finalizes it, right? It's got to be the one that seals it. And I give you an example just of what we are facing and why innovation has had to come along, because it's been years of only having a single solution to protect masts. Here is what is called the lightning COC, which we all know there is no such thing. It's but a test report that is an addendum to the actual certificate of compliance. And this poor installer wrote things that not even a lightning guy understands. A rolling sphere radius of 24 meters. No one understands what that means. An accepted annual frequency of direct strikes to the building of 30. So since when did 30 strikes direct to a building become acceptable? But it's almost, you know, it's doing a lot of work with the insurance industry. We see it's like tick boxes for them. The underwriter wants a certificate, the homeowner has to get it, so they just find someone, you know, some guy in some area that calls himself a specialist because he's been doing it for years. And out comes this, I hereby swear, things are going to be okay. But they're not. And so we see, and we start reading the second page of this certificate, and he says, all material we use are according to the SANS 10313. Now, those that aren't familiar with the standard, it's kind of saying I've built the Ford Ranger to the K53 road rules. You cannot test a product in installation practice. I mean, it's just crazy. But it seems quite okay, you know, 15 years in the industry, this guy has written SANS on his document, but then he goes and he says, we does not take this lightly. And it just gets us thinking, well, if he doesn't even take his COC serious enough to not have grammar mistakes, what did this guy actually take serious, right? And then he carries on writing, and I really got to a funny part where he says, all the lightning conductors carry a workmanship from bending on falling over, apart from when struck by lightning. And he starts saying, well, isn't it the point, right? You're missing what we're trying to do. He says it won't rust for 20 years because it's galvanized, also apart from when it's struck by lightning. And then it maybe start to rust. And it just poses all these things that masts are clearly not the way that is to be used, because it's the way that we've built this, the way that this market has kind of developed through non-regulation, through the insurance underwriters just ticking boxes. We've not done what we are set out to do. We are set out to do risk mitigation, risk management. I laughed at the end when he said, but please be aware of cheap imitations. That was quite funny. He said, well, yeah. But it just shows a case that, you know, we can be as good as we want to, but there's still that element of the installer. And so to start with this, what we've learned and what we've embarked on in a couple of years is that the standards started this problem. And sadly, this is something we have to acknowledge, but gratefully, this is something we as engineers, as a community, can fix. The standards left a lot for intuition. It left a lot for what I think it says. It left a lot for interpretation. It wasn't very clearly spelled out. You know, this is what you do, there's where you start. And so some of the key updates I just wanted to quickly give you is inside the wiring code, 10142 Part 1. In addition, 2.1, we should be published quite soon. Then in the 10313, we actually have quite a few of the working group members here tonight that is rewriting that standard. And then what we are here for tonight is the 62561, which is the product standard, not the K53 I mentioned earlier. Part 8, which has been adopted for about a year now, which is talking about insulated conductors. And this is where we talk about the innovation that has come. In the 10142 part 1, we show clearly that when an external lighting system is installed, it has to be bonded to the earth terminal of the house itself, or of the building structure. Sadly, please, next time you're at a lodge, walk to the mast and see if there's a connection to the house. Almost never. It's never done. What happened there, our problem was, and why we had to address the 10142 is, the electrician said, well, mast is the specialist, and the specialist said, well, DB and bonding is the electrician's problem, and we left this massive hole, huge area that we need to address. We even said then clearly that if you install an external lighting system, you will fit a class 1 lightning current arrestor in conjunction with a class 2 surge arrestor. Also something that's not done. We learned from the electricians and the contractors that their 10142 Annex I, which they have to refer to when they mark surge protection yes in the COC, was so complex. It was written by very clever guys. We know them well, we respect them, but it was perhaps just a tad too far for the contractor. And so we had to simplify things for them. And we've done that, and I'm going to show you some of it tonight. A simplified risk assessment for the contractor to say, if I live in a suburban area for a residential building, I need to know what is the length from the DB board to my kiosk. By knowing that length, I can look at the lightning flash density. Let's assume it's 0 to 5, somewhere like maybe Durban area, maybe a bit higher than Durban. 0 to 5 for a residential building, suburban, incoming line. If that line is longer than 64 meters, a type 2 5KA is deemed necessary. But in higher flash density areas, such as here where we live in Gauteng, 12, 13 meters is already deemed necessary. Just saying that because more lightning events are happening, my exposure of length of cable can be shorter before it becomes a risk that I need and can address. Making it simple for a contractor to read from and say, now I can mitigate. What we did in the 10313 is that we had to write the national standard because the 62305 does not address African problems. It doesn't address thatched roofs, solar rooftop, recreational facilities such as golfing places, oppie-koppies, big concerts. We're working hard at safe shelters, and I look forward to hearing what Chandima has to say about it, because he's part of this group that is also writing something to say, how can we make a shanty home safe? How can we do something towards the taxi ranks, for instance? We're updating the latest ground flash data. And finally, what we needed to do and close the loophole is adopt the new innovations that has now been adopted by both the IEC and the South African national standards. And finally, also, we are mandating the installation safety report to bring back accountability and transparency, because I hereby swear letter that you do get today doesn't hold up in court. And so we need to bring that back. Here's the actual formal report, and you can see it here. And we see one of the issues, talking back to why innovation was needed, says very clearly there that the mast design has to be in compliance with another code, 10225. Now I ask you quite easily, have you seen a lighting pole, such as a floodlight? Have you seen it bent or rusted? No. Have you seen a lightning mast bent or rusted? All the time. Yet the manufacturing standards should be the same, so what's wrong? Right? It's not being manufactured to the right standard. And this is why we have this issue and why innovation has had to come. This certificate gets further and speaks of the designer and the installer bringing an ID number into play, and even a part where he deems himself competent in order to then be liable for what he has signed for. But today we want to talk about the innovation, and just wanted to give you some background as to where we are at and why it was needed. In 2012, the IEC 62305 adopted a new concept called separation distance. Now, separation distance speaks of isolated lightning protection systems. And the idea is you want to not let the current of lightning flow on the structure and or the object you're trying to protect. So by knowing that I could be, let's say, some distance away, I understand that I would be the conductor, it'll go down to earth, and I'll only have a magnetic effect to the structure itself. But now, how far? So we had to figure this out. So a lot of simulations, a lot of calculations was made by multiple national committees, And we finally came up with a separation distance calculation, Ki, which I indicates current, so it depends on the lightning protection level. Kc is the coefficient, so meaning how much of the lightning current is traveling down that conductor. Are they 1, 2, or more? Km is the material which it needs to flash through. Is it flashing through thin air? And we know the resistance of air. Or is it flashing through perhaps concrete? And we know also the resistance value of concrete. And finally, we have the length, which is the top part where we are considering the separation distance, because separation distance at the earth level is 0, and it steadily increases with the length. So the higher the building, the higher the separation distance requirement is. So here's back. My predecessors in the SANS 10313 wrote a very clear statement stating that a mast shall be at least 1 meter away from the grass or any other object, because they did not yet have a separation distance calculation. It was not adopted yet. So they made a very good, very strong statement, and it was used, and we said clearance distance has to be at least 1 meter. When we do the same calculation today, from here to the 3 meter mark, it's about 12 centimeters. If we do it to the top of quite a tall thatched roof, it's 10 meters. It only shows us that we only need about 0.4 meters. So now knowing that we've got actually a lesser separation distance, we start thinking of other methods. And so this is where the cable system called HVRI, high voltage resistant insulation cables, was adopted in part 8, as you can see, one of the component standards, and it is a testing standard to say, well, what do these insulated conductors have to comply to? And you'll see that you have various thicknesses, because we might have various separation distance requirements, all the way from 0 to could even be 1 meter. There one can see lighter units, which can give you 40 centimeter separation distance, longer ones, which gives you about 75, and even for the explosive zone areas, up to 90 centimeters in a single conductor. If one needs more, or one needs to then extend this cable, you would have to have multiples in order to share the current. I think that's quite simple. A project that we've successfully completed, and there's multiples, but one to just show is that the Skukuza Safari Lodge was one of the first that bought into the idea. We worked with the consultancy group Surveyst, and we explained the concept. And you can see that the HVI system was written into the scope of works. And if you look at the design, it really doesn't show well, but there's all these very tall masts everywhere around the building in the traditional way. And then if you look to the left, you've got much smaller, aesthetically pleasing, not as high masts, because what we can do now, this insulator, if it can trap the lightning inside the cable and does not flash outwards, then I can bring the cable straight through an EX zone, flammable area, such as a thatched roof. Because I'm containing the lightning inside this cable, so I can bring the conductor closer to the object I'm trying to protect. By bringing it closer, I can be much lower to the ground, bringing an aesthetic solution. In this case, even if we look at the economic impact, much of the same, in this case, even a little bit more cost effective. I'll show you a video quite quickly. Just, it's, I should start it again. Ready? It's a video just to showcase the process and what has happened, and explains the technology quite well.
Thatch buildings located in high lightning flash zones have always required protection from lightning. The risk of fire as a result of a direct lightning strike and the consequent total destruction of the thatch structure is simply too high. Traditionally, conventional lightning protection methods like the use of freestanding masts have been employed to protect these potentially highly flammable structures. Freestanding mast protection methods are undoubtedly unsightly and often severely detract from the building's aesthetics. Freestanding masts are installed away from the thatch, and therefore they need to be very tall in order to provide protection over thatch structures. Recent research has also shown that these conventional methods have also proven to present other lightning-associated problems, with nearly half of all thatch owners reporting damage to electrical equipment inside the structure. It is now possible, with the use of HVI technology, for lightning masts to be installed directly onto thatch structures. The use of much smaller HVI masts placed directly onto the thatch structure offers the same zones of protection as a conventional freestanding mast. In the event of a direct lightning strike, the HVI technology makes use of what is called the sealing end. This is the mechanism that traps the lightning current inside the conductor. The visual advantages of using HVI masts are clearly visible when compared to older technologies. HVI lightning protection systems have a proven track record of over 15 years. It is the combination of HVI protection systems and the installation of the proper surge protection devices that provides unsurpassed protection from lightning. Our network of master installers are highly trained and experienced in the installation of these state-of-the-art lighting protection systems. Properly designed and installed HVI protection systems comply with the relevant SAN standards, offer better protection from lightning, are easier to maintain, and most importantly, are far more aesthetically pleasing.
So quite nice. Thanks to use the video, Lightning Gurus, at least you sponsored the event. It says a lot more than one could. Here you can see the cable itself, and I'll send it around. The concept is quite simple. In the inner core is the copper conductor that's actually conducting the lightning currents. And then you've got, as you saw, this insulation layer inside. And this insulation layer gets thicker as one would need more separation distance. But the whole trick in this system is, you saw in the video, the sealing end concept, is it needs some distance from when it strikes, where there's a high voltage then obviously excited, where the inner core and the outer sheet, which is semiconductive, needs to become at an equal potential in order to ensure that the lightning does not escape. And it's done by earthing the outside of this mast down to the electrical earth or the Terra itself, and you can see on the inside it's got these feather-like proper bonding onto the semiconductive layer, ensuring then from this point onwards that we have an equal potential between the outer sheet conductor and the inner core, which enables us to trap, as it's called, the lightning inside the conductor. So quite nice. Very glad that we've got innovation. If you want to send that around. The innovation brings to us a point to say we can address a couple of these issues. The first was we never had these installers doing it correctly. Now we have got these manufacturers that only will supply these products to those that have attended their training. So we start picking up the installation quality. That's great. We've got the standards, which is asking for accountability and spelling out quite clearly what we need to do. And then finally, what we've got now, which we've never had in the past, is a product that can be tested, certified to SAB standards. One can produce a certificate for that, which we never had. The masks were, I will manufacture to a standard, which had all to do with wind load bearings and galvanization and how much and how little and how thick the outer diameter of the metal had to be. But one never actually tested it for the conductivity of lightning currents. And so this innovation brings with it a great possibility for us to address now as an application thatch, but also, you heard 15 years it's been in the industry, EX zones, flammable areas, storage tanks, etc. I thank you for your time, and I thank you for the opportunity. Any questions?
Just one question. Alexis, Hi, it's Steve. You mentioned the new certificate of compliance. How's that going to work? Is it going to work like the existing certificate of compliance with the wiring spec? In other words, the contractor would complete that. You said, for example, training would be provided by the manufacturer, but I want to know from a regulatory point of view, because that seems to me a
gaping hole.
It's an elephant in the room, because the existing regulations, where they don't work, it's not the regulation, it's the way that it's enforced and applied that seems to be the problem.
So, but a pretty loaded question. I'll start and dismantle a little bit. So the first part is right now, the only certificate of compliance we have is the electrical one, which means only a registered person by the Department of Labor is allowed to sign. In his certificate of compliance, which lightning protection forms part of, because it forms part of the fixed electrical installation, says that at the end right now, he is the one that takes responsibility, and that electric fences, gas applications, and lightning protection is but a test report attesting to what he has certified. The question to the installation safety report, the only way right now, we don't have a regulator. We believe and dream in one. I also don't think the one we have in the department right now is the best one to follow. We have some hiccups and we need to learn from it, but engage with them, and we are. But what I've seen is we have a good starting point in getting the insurance bodies on board, because the insurance bodies are almost always the ones triggering the need to mitigate their risks. And thatch, of course, being one, but also commercial buildings. Even see it nowadays in solar applications. We are inundated with requests where you said, but the spec says I need lightning protection for the solar system. So it seems that perhaps in some other way, even if it's not their place to regulate our industry, I think the insurance companies can go a long way in helping that, helping us get there, at least, until we have our own regulating body. Any other questions? Mr. Reddy?
No, thanks for the insightful presentation. I just clarity-seeking question. Towards the last slides, where you indicated the mast, or the prison is attached on the rooftop, yes, as compared to the one at a one at a distance. So my understanding, all I want to find from you, has any comparative study show that maybe the innovative way of doing things, it works much better than the other one, and it is incorporated into the standard now?
Well, no. So because the technology is still quite new, I don't think we have enough data to even make such a statement. But if we also remember, we use a method, and we all know lightning well, so the rolling sphere method, protection angle method, to place these rods. So the efficiency in the interception doesn't change. We still apply the same rules, so that would not make it more effective. The only part I believe personally that it is more effective is that it has been tested and proven. Where the mast is, I think it will. There's nothing that shows that it's been in a lab, has taken 100,000 amp strike and survived, or did not allow a flash across. So I think that's the only part where I would say personally that it is a more reliable system, because it has been tested and it has passed these tests.
Thank you, Alexis. The question I have is the HVAC systems that are being used currently, are they manufactured locally? Are they tested locally? And apart from the design tests that one will do to prove the current rating of the system, whether it's a 30 kiloamp or 100 kiloamp type of system, are there routine tests that are done to ensure the manufacturing quality of that system?
That's a great question. So again, two I heard. So the first was, are there any local manufacturers? No, there's not. There are local companies set up that import it. Most of the manufacturers are from Germany. There are strong ones in Poland. There are also the likes of ABB, Den, Obo. These names we know, they all import. No manufacturing has been set up locally. I could foresee it happening, because if we take all the laniness away, it's but an MV-XLPE cable. Nothing else. It's a single core MV-XLPE cable. So one could probably build the manufacturing out of it locally. Now, I'd love to see that, but the demand has got to be there before one's going to jump. The second question was about how to test if it's been in use for a couple of years. Is that what I understood? Or
you do a design test when you prove the design. But after manufacturing, are there routine tests that are done to verify the quality?
Oh, okay, good question. So first of all, the design test is not the part, it's the product itself that gets tested in a lightning laboratory, up to 200,000 amps. These are tested. The way that a laboratory would keep its schema and or TUV or whatever certification they have is there would be random inspections or bundles, 5 out of 1,000 grabbed and then retested. So yes, absolutely. Also, these certificates don't last forever. They have an expiry date and one has to redo because many times with pseudo surge protection, our requirements have changed and then we've got to test to new standards. So yes. Thank you, everyone. That was fun. I'll do it again. That was really nice. Thanks, everyone.
Alexis, just before you go away, we've got a few questions from the webinar.
Oh, yes.
So let's just address those. The first one from Dexter reads, during the risk assessment for the fire hazard of thatch roofs, was a monetary value assigned to it for an area like Kruger Park?
Good question. So there's no mandatory value given for an area. There's a mandatory value given for the risk itself. So a thatched roof is a high risk of fire. So that value is given in the risk assessment. But in the risk assessment, there is a factor N, which is the number of annual dangerous events. And that depends on the lightning ground flash density. But in the standard, maybe carrying on, a risk assessment is even to a point not necessarily needed because we also mandate a certain level also from the start to say it shall be a lightning level 3 and at least that's where you start.
Thank you for that, Alexis. And then the second one from Sianda says, how are the existing installations tested? If tested, what is the frequency?
So I believe she's referring to all lightning protection systems, not necessarily only these. It's a great question because we've debated it at length at the working group. Is 4 years too long? Is 1 year too quick? So we've come to a point to say we need to first find all of the non-compliant, non-effective lightning protection systems. So we're going to embark on a yearly investigation. But we do foresee after that period that the lightning flash density would play a role in how frequent one had to investigate. The IEC 62305 even speaks of the lightning levels, telling us when to do maintenance and when to do inspections. So for now, in order to find a way to remove the ineffective systems, we're embarking on a quite stringent yearly testing, and then we would move to a more relaxed timing period. Good.
Happy days. Alexis, let me thank you very much for that.
Thank you
very much. Ladies and gentlemen, we're in for a bit of a treat this evening because we have not only one but 2 technical talks today. So to that effect, let me not steal the limelight, but I will call Mr. Boytel there to come and introduce the next speaker. Thank you.
Right, hi, good evening. I won't take much of your time since I'm not the main speaker, but earlier this year I took a business trip to Bloemfontein, and I think most of you will agree that that's not the first place you'd expect to find someone from Sri Lanka. But I did. I met a gentleman from Sri Lanka, and since then I've got to know him quite a bit better, and he is definitely a gentleman, but that hides a lot of his accomplishments and his knowledge and his expertise. So I'm not going to read his CV. You would have seen that in the advert. But Chandima Gomes has done a lot of really good work, not only as a researcher. He's presently a professor at WITS, but also as an engineer, and also helping in raising awareness when it comes to lightning safety. And I also know that he's a really good speaker, and I'm sure you'll enjoy his talk. So thank you, Chandima.
Okay, thank you very much, Andreas, for your wonderful introduction, and good evening, ladies and gentlemen. So, Alexis did a wonderful help for me. His presentation is a real precursor to my presentation, and whereas Alexis went into high-tech, I'm going more into indigenous level. So that the title of the presentation is Lightning Safety Measures for Small Structures, both for underprivileged and industrial sector. So my presentation has some overlapping with what Alexis presented. Okay. If you look at the lightning fatalities during the last century, then you will find that in countries like USA and many other developed countries, while the other natural hazards have ups and downs, the lightning has gone down almost exponentially. Okay? However, when we look at the countries with low literacy level, less development, then we see that the trend is the opposite. And maybe you have some idea that in many countries in Africa, during the last few decades, where some sort of scientific lightning research has been started, we have seen that a clear increment of lightning fatalities. This may be due to few reasons. It may be due to the increment of lightning ground flash density, but I'm not very sure about it. But on the other hand, people say that it is due to the sudden burst of population, especially the population burst together with poverty, which exposes more the people into lightning. Personally, I believe that one of the major reasons of we are seeing apparently an increase in lightning hazards or lightning fatalities due to the high level of communication development in many countries. Because few decades ago, if somebody in a village is struck by lightning and got killed, that may be a news only for that village. But today, within one day, it goes to the other end of the world. Okay, now in USA, there's a very popular slogan which says, when thunder rolls, go indoors. Anybody knows the people there? I was without my beard at that time. Then Professor Mary Ann Cooper is there. I think the other two maybe you don't know. But there was a time that we tried to introduce this into South Asia and Africa as well. Then suddenly we got to know a shocking statistic. That is, in Bangladesh, in India, in Nepal, then when we crossed the crossed the ocean, the Indian Ocean, and came to Africa, we found that in Zambia, in Uganda, in Malawi, in many of these countries, 60 to 70% of lightning fatalities have happened while the victims are indoors. Now imagine what a dangerous slogan is this for this part of the world. When thunder rolls, go indoors and kill yourself. And the simple reason, as we see, is that indoor is most often a sturdy building in many developed countries. When we say go indoor, they go indoors into a sturdy building. But on the other hand, in many parts of the world where poverty is dominating, this is a sturdy building, which is simply a temporary hut for a person in a developed country. And now we come to a very important point. Imagine that we have a lightning detection system. We have a phone app. Whenever there's a thunderstorm is approaching, we get a message into my smartphone saying that there is a thunderstorm reaching you. Go indoors. Where to go? What to do? This is one big issue that we came across when we, the lightning activists, try to give solution to the high lightning fatalities in the developing world. And we found that the only option is either to give lightning protection measures to their homes, or we'll have a purpose-made lightning safety structure and ask the people to go inside collectively when there's a thunderstorm approaching. And then we talk to many institutions. We talk to IMF, we talk to Asian Development Bank, we talk to UNIDO. And many of these people, the people who have money, who lend money for the governments, and we even talked to the Indian government, they said that come out with a feasible solution. If you can give us a low-cost solution to protect these buildings, not the buildings, at least the people inside, then we can fund you. So we found that there's a business model in it. Because I'm not talking about 100, 200 protection systems. I'm talking about at least 1 million protection systems only in Southern Asian region itself. I mean, only in that area. In Africa, it may be much more than that. So with this in mind, we came together a few researchers and started doing some research on low-cost lightning protection systems for people who really need lightning protection. And I'm not going to the details of this. And ordinary lightning protection system has usually two parts: the air termination, downcut duct, and earthing system, which we call the external protection. Then, as Alexis said, internally we have to make sure that there are no arcing. So either we bond electrically the LP system into metal parts, or we keep a certain safety separation. And then these are the standards. We have to do a risk assessment and then go for the design. Now, when we analyzed what are the issues that prevents people from adopting these standard recommended lightning safety or lightning protection measures, these are what we came out with. For underprivileged communities, LP system is more expensive than the house itself. Design criteria are too complex. Distance between working environment to a lightning safe structure is too much. Lack of awareness. Then issues with the industrial sector, again, non-permanent status of structures. If you take a construction site, many of the places where the workers stay overnight are temporary structures. You can't give a comprehensive lightning protection system to that. Then space restrictions, they don't have place to do, to come out with lightning protection systems. Challenges of earthing, material theft, distance between workplace again comes, large number of employees to seek shelter, cost benefit concerns. So these are the major issues. And then we started developing these low cost structures. Then we found that we have to define where we stand and what we call as a safety structure. These are the well-known lightning damage mechanisms or lightning injury mechanisms as we have identified. And we thought that at least out of the first 5 of this should be covered in our safety shelters. Whatever the safety measure, safety measures, whether it is low cost or high cost or whatever, we have to protect the people from these 5. And then what about this? Proximity to the strike and secondary effects. So we thought that the proximity, there are 2 issues, the shock wave and the high intensity which causes vision impairity. We thought of advising the people who use these structures regarding what you see there. Then for the secondary effects, again advise, whenever you are having a safety structure, be little bit concerned about the environment. If there is a tree nearby, then be careful, because if the lightning strike the tree, then there can be fire or splinters coming towards you. Psychological effects we could not sort out yet. And then we came up with one design like this. Now you see, if you go for the structures, the single pole type, which Alexis showed very clearly in his presentation, the cost is really high. You have to go to a very large extent. And then he gave a solution. That's why I said that high-tech solution. Wonderful. We all accept that. But then comes the problem of cost. When we cater our focus targets, they are underprivileged people. Or even industrial sector, but they don't want to spend a lot of money on a temporary structure. And with the pipe, the 2 air terminations connected with a catenary wire has an advantage of having a much smaller height. And then we started improving it. And don't forget that there's one very important thing. We always say that at least with the cheapest material that you can find, put a ring conductor around. Maybe a used reinforcement steel bars. This is the best solution for poor communities. So that we applied lightning signals. Let me explain it. Now finally, this is, we have modeled, and So we wanted to see whenever a lightning strikes the safety structure, what would be the potential distribution, what would be the current distribution, and what would be the potential distribution in the area. We conducted the computation for copper, aluminium, and reinforcement steel. And this is just a little bit about our computational parameters. And then we used ANSYS and COMSOL. And then we applied the 50% current parameters. And we found that the electric field distribution and voltage gradient in the LPS and the housing structure and the current density along the conductors. And then first we applied the median value of lightning currents. And then we went to the highest 5% of the values. And we applied negative subsequent stroke, positive stroke, and negative first stroke. And then we found that the maximum potential difference was resulted between the corners of the top ridge of the structure and the adjacent corner of the LPS. And this value does not exceed more than 150 kV. Don't forget that I'm talking about impulse. So this is the peak impulse voltage value. Then potential distribution within the ring conductor remains at levels below any harmful step voltage. Even for the highest 5% lightning current peak values. The maximum value is around 0.2 kV between a 50 centimeter gap. That is usually, we consider the step potential between the feet of a person between 50 to 60 centimeters. However, it is advisable to have a layer of insulation material on the ground, both inside and outside the structure. This is what we recommended. Although we do not consider the safety of people outside, it is important to discuss that. I will go into that later. As the potential gradient outside the protected area could be much higher, you should advise people not to be outside. Now, don't forget that. Can you remember, or did you notice that when I was demonstrating this design, I did not use the word earthing or grounding even a single time. So we are, with the ring conductor, there is some sort of earthing, but we are not recommending, or rather we are not emphasizing that even to measure the earth resistance. The simple reason is we are concerned only about the safety of the people inside, not the people outside. We can go for a comprehensive earthing system, but that will increase the cost very much. And thus there will be no, then we calculated the temperature rise and found that even for 200 kiloamperes, that is the lightning protection level 1 current waveform, 10 by 350, the temperature rise is only about this. Therefore, thus there will be no chance for triggering fire even if the material is flammable, such as thatch. So this arrangement is now we have proven by simulation that can avoid either side flashing, touch potential, step potential inside, and direct strikes. But there is a big challenge still left. Anybody, if you can propose a solution for this, that will be million worth for us. This is something that we are trying to sort out. And then I'm coming to the next type of structures we have developed for entertainment industry, sports industry like golf courses, and even the amusement parks and many other places. A very simple pyramidal structure, just like a tripod. And then we went into further experiments on this. After doing the simulations, we even experimentally tested them. And the idea is that, okay, this is the WITS University HV lab. And so we developed the structure and used an aluminium foil inside with and without an aluminium foil. I will show you the results. And then measured the current waveforms. We applied 10 by 350. Although you can't see, I mean, here we don't apply it, the final product will have 3 millimeter thick PVC cover. It would be wonderful if we can go for the material proposed by Alexis, but it will be very, very costly. And then let me show you something very interesting. If lightning strike this structure, let me say that I apply 10 by 350, 100 kiloampere current. And now, if you look at this point, which is 0.6 meters away from the structure, and this point, 0.6 meters inside the structure, you will find something little scary. This is the voltage waveform at this point, yellow dot, and this is at the red dot. And the difference from here to here is 830 kV. So that means if somebody is outside and his 1 feet is touching the structure, or if he is holding it, then he will be subjected to something like almost 1 megavolt. But on the other hand, inside, without aluminium foil, it is just 210 volts. Don't forget that this is impulse, not AC or DC. And with aluminium foil, it is just 1.2 volts. So inside, the person is fully protected. However, we have to ask him to be away from the metal poles if it is bare. That is where we thought of the PVC cover. Maybe with this technology, we'll improve it further. And this is a structure we have developed especially for boat decks. And this is actually designed with the request of Nat Geo, National Geographic Channel. They wanted to do some filming in the DRC. So I developed it for them. And then this is what we have developed for boating structures. As the time is running fast, I'm not going to the details. So all the dimensions we have checked by simulations. Now, for all these structures I have shown you, before going for a business model, what we are planning is to test, already they are tested against simulation, and now we are in the process of testing them with laboratory high current impulses, and then we are now having a big plan of having triggered lightning camp in Pretoria, most probably in 2020. Now we are having the discussion with CSIR, University of Pretoria, and then most probably we will get somebody from the Florida group, Marcus Rubinstein, who is now in Switzerland. And hopefully we will have a camp next year. And if it is going as we planned, I invite all of you, anybody who is interested in testing your equipment, we will give you the facility. It is for South Africa. So it is open for you all. And then this is another boating structure. And then for mass community, a large number of people, we find the best lightning protection device is an abandoned container, discarded container. You can modify it and you cannot find something better than this for lightning protection. Thank you very much.
Any questions?
Thanks, Chandima. The simulations you ran, never were you taking into consideration the soil resistivity?
Yes.
Or
of
did
course.
you take a uniform value for the area?
Actually, we considered a number of soil resistivity values, but homogeneous. Uniform soil resistivity starting from 50 ohm meters going up to about 5,000 ohm meters. All the calculations I have shown you for 500 ohm meters. But we have to improve it with double layer and multiple layer soil resistivity profiles.
Thank you, Prof. For the personal safety structures, have you considered something similar to what you use for the boats, the guide, stay, or a cable as opposed to a pole, and multiple of them rather than 4? Would it make a significant difference? I think it would lower the cost. That's why.
Yeah. Okay. So now when it comes to these safety structures, we have to compromise between the cost and the safety level. So if we have, say, for an example, 6 rods, then the current distribution is thinner so that it is better. But then we have 2 disadvantages. One is the cost. Other one is the difficulty in implementing it, installing it. Because our idea is to make it in such a way that anybody can erect this within 2 to 3 minutes. So that's the idea.
Would it be possible for you to explain more about the upward streamer effect and how these protection systems eliminate that?
Can you repeat?
The upward streamer effect?
Now, the thing is that when you say upward streamer, I hope that you refer to the upward streamer going from the human body. Okay, so this is something that we assumed at the moment, but now we are modeling it. Because for those who are not familiar with this concept, now whenever there is a lightning step leader coming in the vicinity, many objects around that start sending an opposite streamer towards that downward leader. That goes quite slowly. When I say slowly, in the order of 10 to the power 3 meters per second speed. And you know that current is dq by dt, the rate of change of charge. So that these streamers will not make any harm to the human body, rather than giving you a tingling effect. It's tickling. But the problem is, when the lightning step leader is attached with another answering leader, and when the lightning is over, suddenly the field collapses, so that the streamer formed will again, that will also collapse into ground through your body. And that will happen at a much faster rate, so that the current will be quite high. When I say quite high, it can be like 1-2 amperes. 1-2 amperes flowing for, say, 30-40 milliseconds. That will be lethal. If it is not lethal, at least it can paralyze you on temporary basis. So this is what we call the answering leader or upward leader effect. What we assumed is that when you're inside this metallic structure, the chances of an answering leader going from you is much, much less than you are just exposed to the electric field. And our preliminary calculations, very crude calculations, show that it is the case. However, we need to do proper computation, and then only I can say confidently that, nothing will happen. But until such time, let me accept that we are not very confident about not having a risk.
If you can erect this thing very quickly, that means you don't need to bury the loop around the structure.
Okay, now I'm referring to, when I say erecting within about 3 minutes, I'm talking about the safety structure, not the safety measures for a house. Yes, in this case, that's what I was emphasizing in my presentation. In this lightning protection structure, there is no so-called earthing system. That means when lightning strikes, there will be arcing all over. All over, outward, not inward. That is the important thing. That's why I'm repeating that the person inside the structure is very much safe. No earth electrodes. So if you want to make the outside people also not being subjected to step potential, then you have to go for a comprehensive earthing system. So if you are inside, you are safe. If you are outside, we don't guarantee your life.
Prof, we have one question from Sianda here. It goes as follows. On a rainy day with lightning, do you stay inside the car if you are on the road, or are you safer outside the car? We had the situation on the N3 where there is no structures nearby. Assumption is that there is no lightning protection. Okay,
this is a very popular question. Shall I answer?
Wait.
Okay. Now, usually most of the cars that we know are metallic structures, metallic bodies. So that when you are inside the structure, I don't like to use the word Faraday cage because this is a transient phenomena. But anyway, the lightning, if the car is struck by lightning, most probably the current will be distributed along the body of the car and get earthed through arcing. Okay? Therefore, a person inside the car will most probably be safe. However, there can be punctures in the car. And also, we have reports that in such incidents, the metal of the car has been punctured and the upholstery, the fabric inside has caught fire. Okay, so therefore that's why I always use the word most probably. You will be safe. But if I answer that question, if there are no other safe structures in the vicinity, the best place is to be inside a car. Again, be very careful. Now there are small, especially small cars, which are made of composite materials. And if such a car is hit by lightning, God bless you. Okay.
Okay, Prof, here's the other one. What is the typical grid resistance? That is resistance between the ring conductor and earth.
Okay, I will answer that. Now, the question is that what is the earth resistance of a ring conductor? Okay, so that is quite a big variable because depending on your ring conductor size and soil resistivity, this resistance may have a very small value like say 2 ohms, or maybe it is 1000 ohms. I can understand that question. Maybe the person who asked that question have some thoughts about this. I emphasize that the lightning protection measures that I explain will give the protection to the people inside. So that's why I did not mention about the resistance value. So if it is 2 ohms or 3 ohms, the resistance, earth resistance of the ring conductor, then even the people outside will be safe up to some extent. But if it is 1000 ohms, still people inside will be quite okay, but people outside will be in a pretty bad danger.
Okay, and the one last one here from Jeffrey. He's asking, why does lightning strike players in the playing field when they are surrounded by higher lightning masts?
Okay, now this is a very important point that has been emphasized in the lightning standards. As we know by today, but tomorrow it may be different. As we know by today, no lightning protection system will be able to protect you outside a building. So that if anybody says, I have a technique, I have a lightning protection system, when it is there, you can play football under any thunderstorm condition. According to our knowledge, that is bullshit. Okay, so that there are no lightning protection systems that can protect a person outside. This is a known fact in the standards. Personally, I have some different ideas of that. Even we are now developing a paper, a research paper, challenging this concept. But that's a different story. I can't tell you the work that has been done. I can only tell you what is accepted by the international community. Okay.
In light of no other questions, let me thank you very much, Prof. Thank you very much for your presentation. Ladies and gentlemen, we have come to the end of our technical talks, our very first ST talks, South African Institute of Electrical Engineering technical talks. So, as I mentioned when I started the session, that this is more for networking. So, after the session, once we've concluded, there is some refreshments that are served outside, but use that opportunity to network more than anything else. So I will encourage those that have also attended the webinar to also ask, and when we get through the other areas or other further presentations, please do join us, because that's the opportunity that you're missing, the personal touch, the networking. Then, what we also, I'll use this as a notice opportunity. The very second SAIE Technical Talks session will take place in Witbank. And so watch the space. That's all I will say. On behalf of the office bearers, the president and the CEO, let me thank you all for being here and for your time. And most of all, let me thank you all as the members of the SAIE for making this possible. Thank you very much. That concludes.